All right, guys, so we're finishing up the 2026 FRQ AP Chemistry exam from May 5th. And of course, for this year, we got to finish with 6 and 7, right? So I guess that's the way it's going to go. So we're at the last two questions, right? Each of these questions are worth 4 points apiece. So if we look at question 6, we had one prompt, two prompts, and or 1, 2, 3, and 4 prompts. So we had 4 prompts. So we know that each point or each prompt is worth 1 point. So if we have to answer and explain, it's only worth 1 point, right? So just kind of understanding that. Now, when I first see absorbance versus concentration, I'm thinking Beer's law, right? I'm thinking maybe maybe I might have to use Beer's law. And if I need to calculate E, the molar absorptivity constant, um, that's just the slope of this line. So maybe I'll have to do that, just, thinking out loud. But remember, they gave us a good, nice chart here. So a lot of times, like, we can just go to an absorbance value and then go over, to where it intersects the line and then go down here to get our molarity value, right? So, that's what this question ends up being, just kind of consulting this graph. And, if this is your absorbance, find your molarity and that kind of thing. But, just things that we could do. All right. So the student measures an absorbance of 0.32, so that's this axis, of V2 plus. The concentration of V2 plus ions in solution is represented by a particulate diagram down here. So they're saying, okay, so when the absorbance is 0.32, this is what the cross section of our solution looks like. It has 1, 2, 3, 4, 5, 6, 7, 8 ions in it. Okay. So what I need to do is I need to find 0.32 on the graph. I need to go down here and see what molarity that is. So 0.08. Okay. So it makes sense, right? So the molarity is 0.08 right now, and they drew 8 particles to represent a 0.08 molarity. Okay. So that's kind of something to note, right? So if absorbance is 0.2, the molarity is 0.8, and how do they represent it? 8 V2 plus ions in that picture. Okay. Now this is an annoying question because we're going to have to keep going back and forth. All right. So if we go to this, it's saying, go back to the question. It's saying in this diagram here, we have to draw what the picture looks like when the absorbance is 0.08. And so this is where it could get confusing, because the initial absorbance they gave us was 0.32, and that translated to a 0.08 molarity. But now they're saying now the absorbance is now 0.08. So we got to figure out what molarity that is and then draw the particulate diagram, right? So if we find, what was it? 0.08. So we got to find 0.08, which would be right here on our chart. We go to where it intersects the line. So the molarity is 0.02. So when the molarity was 0.08, we drew 8 particles. So when the molarity is 0.02, we should draw 2 particles, right? So you just had to draw 2 dots in there, right? Let's see, let's go to the key, right? Right, so the absorbance at 0.32 had a molarity of 0.08. The absorbance at 0.08 had a molarity of 0.02. So the picture with 0.08 had 8 of these. So the picture with 0.02 should have 2 of them. So you just need to draw 2 dots there and you get your point. Okay. All right. So now we go to this next question. So the student measures the absorbance of a different solution. So they don't know what its molarity was. So they want to measure its absorbance, and they want to use this chart to figure out, okay, based on this absorbance reading, what's its molarity, just like we did with the other ones, right? That's what they're trying to do. Okay. But the absorbance is 0.36. And if we go to the chart, if we go to 0.36, right? So, right, it's the upper limit. So we can't really be sure of what the molarity is going to be. Okay. All right. So what did they do? They took this solution that the absorbance reading was too high, and they diluted it to a new known molarity, or they diluted it to a new known volume. And then they measured the absorbance of that, knowing it would bring down the molarity, the absorbance value enough that we could figure out the concentration of the diluted solution. And then we could do M1V1 equals M2V2, but in this case, calculate M1 to figure out what the undiluted solution that had this absorbance must have been, okay? So kind of a roundabout way of thinking about this question. So in part one, the absorbance is diluted, of the solution is diluted to 0.22. The absorbance value is 0.22 to determine the molarity of V1 in the diluted solution. Or that's what we have to determine, right? In the diluted solution. So the solution that didn't produce this absorbance value, but we diluted that solution and now it's producing that absorbance value, right? So we're going to go to our chart and we're going to find 0.22 on the absorbance chart, okay? And we're going to go over to where it intersects, and that's 0.055. So that's our answer to part one. It would be 0.055 molar, right? And that's just using the chart. Okay, so let's see if we got that one. Yep. So when the absorbance is 0.22, the molarity is 0.055 moles per liter according to our chart. So that's part one, okay? So understand what we did, right? So that was the molarity of our diluted solution, right? So, and M2 and V2 are our diluted solution, and M1 is the molarity of the solution before the dilution. Well, what did we do? We took 3 milliliters of the undiluted solution, so that's why V1 is 3. M1 is what we're solving for, okay? And we just figured out the molarity from the chart, and we diluted it to 25 milliliters in a 25 milliliter volumetric flask. So all we have to do is solve for M1, and that would be what the molarity of that solution was. So it comes out to be 0.46. Okay. All right. So part C is the concentration of V2 plus calculated in part B2 is lower than the actual. So we got 0.46, okay, when we calculated what the undiluted sample should have been, okay? And the student is saying that that's probably because when they were diluting that solution, they went over the line on the volumetric flask, right? They went over the line on the volumetric flask, okay? So what did that mean? They added too much water. They diluted it more than they should have. So the molarity went down more than what they thought it did, okay? All right. So the question is, the student claims that the calculated concentration is too low because during the dilution step, the final level of the solution was higher than the mark on the volumetric flask. Do you agree that this could be why this calculated value is less than what it should be? Okay. And you should agree, okay? We added too much water, which diluted the solution, right, more than what was reported, right? So we thought we diluted the solution to this molarity, but we really diluted it more, right? So we would agree we added too much water when we diluted the V2 plus solution. The absorbance, therefore, the absorbance of 0.22 for that solution was too low. Therefore, the molarity that we plugged in the M1V1 equals M2V2 was also too low. So when we solved for M1, it was too low, okay? So we agree with that student, okay? All right, that was question 6. On to question 7. Let's look at question 7. Question 7 has 1 prompt, 2 prompts, 3 prompts. So if we go to the point, we have 3 prompts. One of them's worth 2 points, okay? And now let's get to the question. All right. So I'm given a reaction, okay? I'm given the delta H of the reaction. It's negative. I know it's exothermic. okay? I'm given molar heats of formation. So maybe I'm thinking on my formula sheet, I might have to use this equation, right? Delta H of reaction equals delta H of formation of products minus the sum of the delta H of formation of reactants, right? So maybe I can use that, okay? Right, remember elements are always zero. A lot of times they don't remind you of that. They don't tell you that sodium solid and O2 gas would be zeros, and you got to know that, okay? But they told you that, so that's good. All right, and for part A, all they're asking for is what's the delta H formation of this thing, okay? So we could use this equation, right? We could use this equation. It's not going to take us that much time. And do products minus reactants, and we're solving, and we know what the delta H is equal to, so we would say negative 828 kilojoules equals 2 times X minus 0, right? Because our reactants have a sum of molar heats of formation that add up to 0, okay? But a quick way, and not that using this equation would be much slower, but if you were like, wait a minute, this is showing the formation of 2 moles of this compound from its elements. If I make it show 1 mole of the compound being produced from its elements, that's what delta H of formation is. It has to show the formation of 1 mole of a substance from its elemental components. And that's what this does, but this is showing 2 moles. So all I really had to do is divide this by 2, right? And that's what you would end up doing if you plugged it into this equation. So, maybe you saved yourself some time, and you were just like, oh, I just do the delta H reaction divided by 2 because the reaction is showing 2 moles of this being produced, and I just need to know how much energy for 1 mole being produced, right? So the answer comes out to be negative 414 kilojoules per mole, okay? Then in part B, it says 18 grams of sodium react with 12.8 grams of oxygen, and we want to know how much heat can be produced. Show the work that leads to your answer. So this is just limiting reactant stoichiometry because we have an amount of both things. Now, if you're thinking about it, right, it's about moles, and you have 18 grams of sodium, and you would be dividing 18 divided by 22.99, which is sodium's molar mass, and you would dividing 12.8 divided by 32, which is oxygen's molar mass. So you have less moles of oxygen. And so a lot of students are going to think oxygen is limiting because you have less moles of it. But remember, the coefficient of sodium is 4. You're going to consume 4 moles of sodium, but you only consume 1 mole of oxygen. So maybe the sodium is limiting. So it's probably, don't just go, I think oxygen is limiting. I just have to use that information. I don't have to waste my time worrying about what sodium's going to do, because if you did, you would get that wrong. So you gotta be careful with that, right? So again, it's limiting reactant stoic, okay? And I have it almost set up, right? But there's one missing step here, is I would have to be dividing by 4, because it's this much energy for 4 moles of sodium, not that much energy for 1 mole of sodium. I probably have it better on the key. So here would be the stoichiometry for the sodium. So if all the sodium reacts, you're going to get this many kilojoules produced. If all of the oxygen reacts, you're going to get this much. So how much can you get? You can only get 166 kilojoules. The sodium is limiting, okay? So they asked the question, how much energy is released, so you can report a positive value. If they asked what the energy change was, then it would have to be negative, because energy is being produced, it's being released, because it's exothermic. But you didn't need that in this case. I think if you put negative 166, I think that should be okay. It's redundant, but I think it should be okay. All right. And then part C. All right. So remember, they give us lattice enthalpy, lattice energy. You can remember, you should kind of equate that to melting point of an ionic solid, right? So the higher the lattice energy, the higher the melting point. What does that really mean? The stronger the ionic bond. And what are ionic bonds based off? Coulomb's law, right? And so when you read this question, it even says using Coulomb's law. Explain why this has why does sodium and oxide have a stronger ion-ion bond than rubidium and oxygen? And when it's ions, it's always Coulomb's law, Okay. So remember, you get Coulomb's law in your formula sheet. Let's find it. I think it's at the beginning, right? And you don't get the equal sign. So you're never going to, on the AP exam, you're not going to have to calculate the force of Coulombic attraction. You just have to know, is it going to be higher? Is it going to be lower? And what does it depend on? Q1 and Q2, which are the charges of the two different particles, ions in this case, divided by r squared, which is the distance between those particles squared. So the closer they get, the higher the Coulombic attraction, the stronger the Coulombic attraction. The higher the charge, the higher the Coulombic attraction. Okay, well, when we look at the ions that we're comparing, they're the same charges, right? Sodium ions are +1, rubidium ions are +1. Oxide ions are -2, that oxide ions -2. So the magnitude of charge isn't at all the same. So it's about how close they can get to each other, and that's about the radius, the ionic radius, okay? And what we just need to understand is rubidium has a bigger radius than sodium. So sodium ions and oxide ions are going to be able to get closer to each other than rubidium ions and oxide ions. And so because the opposite charges are closer, they have a stronger attraction. They have the same overall charge. So in terms of magnitude of charge, the Coulombic attraction is the same, but it's because those charges can get closer to each other because the sodium is smaller than the rubidium, okay? So you would say the Qs are the same, right? Rubidium has a larger ionic radius than sodium ions. So that means sodium ions and oxide ions are closer to each other. They have a stronger Coulombic attraction. As distance between charged particles decreases, attraction increases. That's what Coulomb's law is saying. Okay. So that's it. End of exam. You did it, or one of my students did it. The rest of them are going to do it on May 20th. But if you were a student not at Whispering and then took the test on May 5th, congratulations, you did it. And hopefully you got all the right ones, and hopefully you didn't make the mistakes that I made, when I was doing it. But, when I do it, I try to go through it as fast as possible, because I kind of want to see where, if you're not paying close attention, what are the mistakes that you might make, So it's always a good lesson to learn. Anyway, that was the AP exam for 2026 for at least the free response. And one thing to notice is there wasn't really much kinetics on here. I guess there was. There was the, yeah, there were, I guess this was kinetics, but it really didn't, yeah, okay. So there was a couple kinetics, so never mind. I forgot about that one. But maybe there were a couple more kinetics questions on the multiple choice. But kinetics isn't, kinetics really isn't represented that much on the AP exam. You'll get a couple questions on the multiple choice and the free response. So seemed pretty straightforward. A couple of kind of, questions that, like setups that you're used to seeing, but just asking about different parts of it that you're not used to asking, just kind of, so you could get hung up if you got caught thinking about stuff a little too much. So again, one of the big things about the test is to not get trapped in spending too much time on one question. Okay. So anyway, have a good one.